Hello, and welcome to our Optologic how-to video series. Today, I'll be showing you how to take advantage of network transportation optimization. More specifically, I'll be showing you how to take advantage of running Hopper within a NeoSolve. I'll show you the inputs required to do this, the process to make it work, and I'll show you the outputs you can expect to see to support your analysis. First, let's take a look at a couple of examples in which this might be important for one of your use cases. So Hopper within Neo allows routes, including multi-stop routes, to be considered as inputs during a Neo optimization run. Instead of optimizing flows using only point-to-point lanes, Neo can now evaluate the full cost and capacity of routes when deciding where products should flow. This is especially powerful for use cases like customer consolidation and hub optimization, where using the traditional Neo solver by itself might ignore some of the potential cost savings you could have by incorporating multi-stop routes. For example, instead of two distribution centers each serving one customer respectively based on geographic proximity, the combined algorithm may find it cheaper for a single DC to serve both of those customers on a multi-stop route, even after accounting for route costs and vehicle constraints. For hub optimization, consider a situation where you have multiple suppliers serving one distribution center. In a traditional NeoSolve, it might be more cost-effective for each supplier to ship directly to that distribution center. However, when we consider a multi-stop route, it may make more sense from a cost perspective to send all of our shipments from our suppliers to a centralized hub and then deliver to the distribution center. Now that we understand a couple of the common use cases for running Hopper within a NeoSolve, let's look at the inputs required to make it work. We have a sample model here that you will be able to find in the resource library. Our model is called Network Transportation Optimization, Hopper within Neo. In this model, we have all of the basic tables populated to support a standard NeoSolve. In addition to that, we've included some of the additional tables that you would typically use for a Hopper solve, and I'll show you how to connect these Hopper inputs to your network optimization inputs as well. The first table we're looking at is the transportation rates. This is where we define some of the costs associated with the multi-stop routes that we want to consider as a part of our NeoSolve. As a part of running Hopper within Neo, we can also include transportation assets. In this case, we have defined one large vehicle asset, and we have tied the large vehicle rate from our transportation rates table to this asset. As a part of running Hopper within a NeoSolve, we can also define shipments. For the sake of simplicity, we have not defined our own shipments in this sample model. By default, the solver will create records for each customer product pair and their two closest sources. Now I'm going to show you the inputs required to connect these to your network optimization solve. We have a table called Transportation Route Planners. In this table, we have defined one route planner name called Route Planner 1, and we have chosen a route planning method called Hopper. The Hopper route planning method allows the solver itself to define the different routes that will be considered as a part of the Hopper solve within the NeoSolve. For simplicity's sake, that is the method we have chosen today. However, we also have the flexibility to choose a fixed route planning method. When using a fixed route planning method, we have two additional tables that we can use. We have a fixed routes definitions table, where we can define the fixed route name and the sites associated with that route. And then we also have a fixed routes table where we can connect our fixed route name with our route planner name from the transportation route planners table. This is what connects our fixed routes with our transportation route planner. Finally, we need to connect the transportation route planner to our actual transportation lanes in our network optimization model. We're going to do this in the transportation policies table. Now, in this table, you can see that we have defined several lanes as a part of this network, and you can see in this mode name that we have separated out multi-stop versus direct. And if I filter for multi-stop, and I scroll over to status, I can see that all of these are set to exclude by default. And I can also see that they are all tied to our Route Planner 1 record. This means that when we go to run this model for the baseline, these records will not be included, but we'll be including these records through scenario items. Now that our inputs are all ready to go, let's look at our scenarios and how we're going to activate our hopper within Neo. And here you can see that we have 4 scenarios built. Our baseline direct only is what will happen if we run without any changes. We have a baseline multi-stop only, in which we are using 2 scenario items. One, to include our multi-stop records in the transportation policies table, and one to exclude our direct delivery records in the transportation policies table. This is going to force all of our customers to be on multi-stop routes. Finally, we have a baseline direct and multi-stop. All this does is it turns on our multi-stop transportation policies without excluding the direct transportation policies. We also have a scenario item that forces each lane to choose one of these modes, meaning each customer has to either choose a multi-stop or a direct delivery. Now that we've looked at how these scenarios are set up, let's take a look at how our results look when we run. Once our scenarios finish, we can navigate back to our output tables to look at our results. First, I'm going to look at the optimization network summary table. In our optimization network summary table, we can see the total supply chain cost associated with all of our scenarios. As you can see, when we are only considering direct delivery to our locations, meaning we're not considering multi-stops as a part of our network optimization solve, we can see that our total supply chain cost is about 144 million. When we consider multi-stops, we see that number drop by about $4 million. And furthermore, once we allow the solver to choose whether it's best to use direct or multi-stop, we can see a further savings of nearly $3 million. If we dig into the details more, we can look at how this is actually impacted by transportation cost and multi-stop route costs. If we want to look at a specific example, we can go to our optimization flow summary. In this case, I'm going to filter for one customer just so that we can see how their experience changes based on the different policies we're choosing. So in our baseline direct only, we can see that CZ215 is served by Salt Lake City, DC, and it is served direct. When we include multi-stop only, we can see that this CZ is still served by Salt Lake City, DC. However, it is now using the multi-stop mode. When we allow the solver to choose whether it is best to use multi-stop versus direct, we can actually see that the solver thinks it is better for this customer to be served by Salt Lake City, DC directly if that is its source. And finally, if we look at the scenario where we allowed optimal DC assignment, we can see that this customer zone is actually included as a part of the multi-stop route from the San Bernardino DC instead. Finally, we can look at the optimization flow route summary, where we can find the CZ and we can see which multi-stop routes it was on for each of those multi-stop scenarios. This is just a brief example of how you can take advantage of using Hopper within a Neo solve. I hope you found this video helpful, and please go take a look at this for yourself within Cosmic Frog and try it out. Thank you.